All right, let's go ahead and continue with our topic of confidence intervals. So far in our discussion, we've stated that the true mean, the true population mean, is going to be between our sample mean, x bar, and I'm going to subtract my margin of error. So that's the margin of error for the mean, or the error bound for the mean, EBM. And here we can see it's the same analysis here. We take the sample mean, and this time we add our error bound. And remember that this, really, you just want to think about it as the number of standard deviations times the actual length, right? The actual variability, and that's the standard deviation. All right, let's go ahead and demonstrate an example on how we can use this. Now, there's actually two things here that I want to note, and that's that we kept z sub alpha over 2. And remember that that basically tells you that your sampling distribution x bar has a normal distribution. And not only that, but we have sigma, which is a population parameter. So sigma is a population parameter. And just like the the population proportion, it's a value from the population, and we don't know it. But here we have one of the first cases, which is, can you make a confidence interval assuming that that parameter is known? And this is a very strange sounding assumption because remember that the variability is essentially what the standard deviation measures. So if you don't know the center, it's kind of strange to make it seem like you know the standard deviation, the population standard deviation. But it is actually kind of reasonable if, for example, you're looking at data that has a lot of historical evidence attached to it. So one could be something related to either animals, traits of animals, for example, the length of, let's say, a dolphin that has been studied for various years. We can also look at, for example, lifespan of humans has also been studied over various years. So a lot of variables of interest have extensive historical records. And because of that, we have a fairly good idea as to what that variability is. One example that I like is, for example, calibration. Like if you're measuring how much, let's say, um, uh, um, how much liquid would fit in a cup, whatever device you use to measure, if it's a scientific instrument, that variability is known because all of that is produced within certain specifications. Anyway, this is going to be our first example where we go ahead and say, let's create a confidence interval, assuming that the population parameter sigma is known. And so I'm basically going to go ahead and use my sample. Let's emphasize what comes from the sample. So X bar comes from the sample, and so does N, that comes from your sample size. Sigma is going to be given to you. We're going to assume that you know it. And then therefore, if you have a significance level or a critical value, then we can go ahead and compute the interval itself. So here's our first example. Allen's hummingbird, scientific name Selaphorus assassin, is a species of hummingbird, pictured here on the right, which breeds in the Western United States and has been studied by zoologist Bill Arthur. A small group of 15 Allen's hummingbirds has been under study in Arizona. The average weight of the birds is X bar equals 3.15 gm. Based on previous studies, we can assume that the weights of Allen hummingbirds have a normal distribution with sigma equals 0.33 gm. Let's construct a 90% confidence interval for the average weight of Allen's hummingbirds in the study region. I wonder if that's supposed to be mg for milligrams. But anyway, let's go ahead and note that they told us the population standard deviation. So we know that. And we want to construct a 90% confidence interval for the weights of the hummingbirds in this region. So we're going to assume that the 15 hummingbirds are a sample. Now, this is very important. It says what conditions are necessary for us to compute the confidence interval. And you got to remember that the conditions that are necessary is that we meet all of the sampling requirements to obtain something which looks like this in our sampling distribution. And so those requirements are fairly simple. Obviously, we need a valid random sample, a genuine random sample. And because we have a sample here that a group of 15 hummingbirds, if anybody is doing any kind of science, we're going to assume that they understand the importance of this. So we can go ahead and assume that we have an actual valid sample. The next thing that we need is we need to make sure that the random variable of interest is normal. So let's go ahead and write that down. The random variable of interest is normally distributed. And notice that they did tell me here that Allen hummingbirds have a normal distribution. And that should be a space normal distribution. All right, so we know that my data follows a normal distribution. So that way, if I take samples of size 15, the sampling distribution itself is 15. So this is enough to tell you that X bar is also going to be normally distributed with center of mean and standard deviation sigma over square root of n. And that comes from the central limit theorem. All right, I believe that that's more or less all that we needed. You also need independence of the hummingbirds, but we'll get into that a little bit later. But these are the two major ones. We want to make sure you have a genuine random sample and your random variable, which in this case is the weights of hummingbirds. So the weight of the hummingbirds is known to be normally distributed. Now let's go ahead and find this. This is what is the margin of error? So we got to remember that the error bound for the mean is given by z sub alpha over 2 times, so this is the number of standard deviations times the actual standard deviation. And notice that all of this information we have. So let's just write this down. Sigma is 0.33. N is my sample size. And in this case, my sample size is 15 because we only have 15 hummingbirds that we're looking at. So if I were to take samples of 15, I know from the previous section that I can determine the variability in the sample means. All right, the last thing that we need is this value right here, z sub alpha over 2. Notice that the problem does say 90% confidence. So therefore, that means that alpha, the significance level, is 10%. So that's 0.1. Visually, we did this in previous problems by writing this normal distribution and then shading 0.9. Sorry about that. And shading 0.9 of my region. And then in the tails, I have 0.1. So alpha over 2, which is a single tail, is going to be 0.1 divided by 2, and that's 0.05. So therefore, I can go ahead and find that critical value, z sub alpha over 2. Let's just go ahead and do that real quick in StatCrunch. We go to stats, calculator, normal. Mean is 0, spread is 1. I don't know the value, but I do know the area to the right should be 0.05. Hit enter, and we get our value 1.645. So my margin of error is 1.645 times 0.33 divided by the square root of 15. So we can throw that into a calculator. And in this case, I'm going to type it in. So that's 1.645 times 0.33 divided by the square root of 15. And we get our standard deviation right here, 0.1402. So that right there is my margin of error. And remember that what this basically is, it now says if we follow our formula up here, so let me write it down. My confidence interval, doing this by hand now, is take your sample mean and you're going to subtract the error bound. And then you're going to do the same thing. Take your sample mean and now this time you add the error bound. And you're going to get two values. So let's go ahead and substitute here. X bar is my sample mean. That's 3.15. And then I'm going to subtract this value, 0.1402. Do the same thing for the right-hand side, 3.15. This time we add 0.1402. And we can go ahead and use a calculator for this. So I'm going to copy paste this number, or here, let's just type it in. It's 3.15 minus gives me 3.0098. And if you do the plus, change this here to a plus, you end up with 3.2902. And there you have it. What we created now is we are saying, if I were to take a single sample, so here's a visualization. If we were to take a single sample, we're going to say, I'm fairly certain that I'm going to land close enough to the middle. So here's X bar. And then if we extend to the right from this number by the error bound, and we extend to the left by that error bound, that wherever we land, whatever value we get on this number line, will capture the true center mu. So that's what we want to go ahead and interpret. So here when it says interpret, we're going to say we are 90% confident that the true, I don't know why this keeps moving. And remember that here what we're trying to capture is that this interval captures mu, which is the true population mean. And you just basically say what it is that you were measuring. And in this case, it's the weight of Allen's hummingbirds. So we are 90% confident that the true population mean weight of Allen's hummingbirds is between these two numbers, 3.0098 and 3.2902. So this is amazing because you're essentially saying from my sample of 15 birds, I have a fairly good idea as to what the true population average of all of the birds in the population is between. And that's between 3.098 and 3.2902. So there you have it. That's our first full example for our confidence interval. And notice that in terms of a visual, it actually does make a lot of sense because we're basically saying if you know that this is how samples are going to behave, right, that they're going to follow this pattern, taking a single sample, you are fairly certain you're going to land close enough. So if this is X bar, that if you extend to the left a certain amount and you extend to the right a certain amount, that you'll get an interval which captures the true center here, mu. So it really does depend on that concept of saying, I know how sample means are going to behave, which allow you to create this interval. All right, that's the only one of the only times we're going to do this by hand. What I want to do is I want to show you how to do this using technology. It's very simple. To use technology, you're going to go ahead and use stack crunch. And you're going to have to be careful here. You need to know that sigma is known. And because sigma is known, I'm going to be using what's called a Z interval or a Z test. Here are the technical requirements. We already mentioned some of them. That was the simple random sample and our shape requirement, which was that X had to be normal. We didn't really mention independence, but that has to do with probability. So we'll keep seeing that in a moment. And also standard deviation has to be known. So sigma has to be given. The theory that we developed basically says that creating this interval, these two values, will give you the what you need. So let's go ahead and use StatCrunch. To use StatCrunch is actually very easy. We'll simply go to Stats, and then we go to where it says Z-Stats. And we have the values given here. The reason that it's Z-Stats is that my formula uses the Z distribution. So we see that right here. Anytime you're using something that is based off of the Z distribution, you're going to go to Z-Stats. So here I'm going to go to Stats, Z-Stats, and then the rest of this should be self-explanatory. Like, do you have one sample or do you have two samples? And in this case, you realize we have a single sample of 15 birds. And you don't have data. For example, I don't have a spreadsheet full of information as to how much bird number one weighed, how much bird number two weighed, and so on. We only have summary statistics. So we're going to select with summary. Then you'll see the following come up, and it's going to say, what does your sample mean? Go back to the problem and recognize that your sample mean is here, 3.15. And notice that it just says standard deviation. It does not say sample standard deviation because you're assuming that the standard deviation is known. It's 0.33. And then finally, my sample size, which in my case was 15 birds. So a small group of 15 birds. All right, then we're going to tell StatCrunch perform. Hypothesis test is what's going to come up later. But for now, we're going to do a confidence interval. So select confidence interval and change the level to the level that was described. In our case, it was 90. Verify that here. That is all that you need. Press compute and StatCrunch will carry out the exact same procedure that we just did by hand. So take a look at the following. Standard error, 0.0852. That should look familiar. We didn't really do it, but it's what you would have gotten if you carry this out. So let me show you. Sigma divided by square root of n, that's the standard error, because that's the variability in the sample means. So if I press 0.33, which was sigma divided by square root of n, we get 0.8520. So we can get that information right there from StatCrunch pretty easily. Now take a look at this. Lower limit, 3.0098. 3.0098. Upper limit, 3.2902. 3.2902. So StatCrunch is able to perform this very, very quickly without having to do this intermediate step, which is where students mainly get confused. So we're going to be using StatCrunch, so I will expect you to write out this interpretation and to perform the check of the requirements since we're not really going to be doing much computation. So we can verify that here, that this gives me sigma over square root of n, and that this lower limit here is the lower bound, and this right here is the upper bound. Now, why are there two of these? One sample Z, one sample Z summary. Oh, okay. Let's go ahead and continue. So this was the standard error. Notice that my formula was x bar plus minus Z sub alpha over 2 times sigma over square root of n. So we got sigma square root of n, we got x bar, that's right here, sample mean. And it looks like we have everything except z sub alpha over 2. So we can actually get z sub alpha over 2 in StatCrunch. That's this right here. So there's the rest of this matches. Here's x bar, here's sigma over square root of n. Here's the lower bound and your upper bound. And so if you go back into StatCrunch and you say, hey, I want to know what z sub alpha is, you can click Options Edit. And then where it says the output, select Show Critical Value. And if you select Show Critical Value, it'll show you z sub alpha over 2. Take a look at this, 1.6448. When I did this by hand using StatCrunch, the StatCrunch calculator, I got 1.645. So this definitely does agree. 1.644, but because of the 8, we round up. All right, there you have it. We have our full example, and this is how we're going to do it. So I want you to go ahead and see if you can create the 95% confidence interval for example 2. So go ahead and read this problem carefully, and we'll go ahead and complete these together when we return. All right, so let's go ahead and answer part A. Create a 95% confidence interval. So I hope you read this, and we can see that we have a sample of size 31. We have a sample mean of 80.0, and we have a population mean of 2.0. That's more or less all that we need because now we just need the confidence level. So let's remember that we need to go to stats, Z stats, one sample with summary. We type in our sample mean. So what was it? 80.0. Standard deviation, which if you remember was 2.0. And my sample size, which is of 31. Select confidence interval, update the level. Ours is 95, so we're going to leave that alone. And if you want, you can also select show critical value. Hit enter, and note that our answer is here in lower limit and in the upper limit. So we can go ahead and write this down. So 75, 79 point, let me round this to one decimal, so I'll just leave it at 79.3, comma, the other value, 80.7. So know that we can interpret this by saying that the true average preferred height for all experienced typists is between 79.3 and 80.7 centimeters. I believe this had to do with keyboards. So the actual height of preferred is 79.3 centimeters and 80.7 centimeters for all of the experienced typists. Now let's go ahead and answer this question here. This one's more theoretical. How can I create a wider confidence interval? So notice that the width of the confidence interval is basically saying if I were to visualize this, here's your center. How can I make this go further out? To the left and to the right. And we got to remember that this is the error bound. The error bound for the mean, which has the formula z sub alpha over 2 sigma over square root of n. So there's two ways that we can do that. And it's just a mathematical reason why. If you want this to be larger, then you want this quantity here to be larger. And one way to do it is to increase Z alpha. So let's go ahead and think about how we can do that. Remember that Z sub alpha said what is your confidence level. And Z sub alpha basically tells you how far you go from the center. So if Z sub alpha is larger, so one is to increase Z. And so the way to do that is to push this further out. So what that means is you want to capture more of the data, which means that you want to include more of the observations. So the way to increase E sub alpha is actually to increase confidence. Increase the confidence level. The other way to do it is to make this value right here divided by square root of n to be smaller. If you divide by something smaller, you get bigger values. So the other one is to decrease n. Take a smaller sample size. That will introduce more variability, so it'll increase the error bound. We can go ahead and get opposite results if I'm asking, what if I want a narrower confidence interval? So if you want the error bound for the mean, if you want this to be smaller overall, then there's a few ways to do that. One is to make this value smaller. So think about how to do that. So here's a visual. All right, that tells you how far to go from the mean. So you would decrease how far out you go, which means that you capture less of the actual samples. So that means that you decrease the confidence level. And finally, the last one is if you want this to be smaller, you can increase n. All right, and again, both the reasons for this is that is purely mathematical. So we want to remember that our error bound is given by this expression. All right, that's it for our video. If you have any questions, please make sure you reach out.